Friends, let me show you a question that one of you asked me. Well, you can see the question on your screen and it's a very fundamental one. But in some way, it points towards a mathematical paradox that collapses our entire number line. You can prove that -1 equals 0. You can also prove that 1 equals 0. You can also prove that 2 equals 0. And finally, you can even prove that 1 equals 2. This means that all the numbers on the entire number line become equal to each other. Well, where is the mistake in this paradox? And if this paradox is correct, then why is it correct after all? Well, today in this video, we will discuss all the details about it. So, as we have already talked about Euler's identity before, actually, the origin of this paradox lies in Euler's identity. E raised to the power iota pi equals -1. I hope all of you are familiar with this equation. If not, then let me simply define it. This is a masterpiece of mathematics. This means that when you use the exponential function with a complex number, it gives a negative number. How? Because e raised to the power iota theta is equal to cos theta plus I sin theta. So when the value of theta is pi, then e to the power iota pi equals cos p plus iota sin p. Cos pi is -1 and sin pi is 0. That's why the answer we get is -1. Up to this point, everything is correct, but now comes the real twist. A paradox that will collapse the entire number line. Now look, the question asked in the comment section also starts with this very identity. E raised to the power iota pi equals -1. Now what did we do in the next step? We squared both sides, so e raised to the power iota pi, the whole squared, equals -1 squared. So what will this become? E raised to the power 2 iota pi equals 1. Well, this statement is also absolutely correct because the square of -1 is 1, and in complex numbers, e raised to the power iota. 2 pi is cos 2 pi plus iota sin 2 pi, and if you put in the values, you'll get 1. Now what did we do next? We know that e raised to the power 0 is always 1, so in place of 1, we'll put e raised to the power 0. So in this case, we'll compare and write e raised to the power 0 in place of 1. So our equation will become e raised to the power iota 2 pi equals e to the power 0. So now, if the bases in this equation are the same, then their exponents will also be equal. This is a fundamental property of mathematics. That means 2 iota pi will be equal to 0. Now we know that 2 pi cannot be equal to 0. So this means that iota must be equal to 0. But we know that iota is equal to the square root of -1, so this means the square root of -1 will be equal to 0. From here, you can conclude that I squared, that is, the square of the square root of -1, which is -1, will also be equal to 0. And when you square that as well, you will also prove that 1 is equal to 0, and then you will even prove that 2 is equal to 0. But I mean, how is that possible? If all the numbers on the entire number line are becoming equal to each other, then it means something is definitely wrong here. Because this only happens when your entire number line collapses, and the number line collapses only in certain cases. For example, when you allow division by 0, if you allow division by 0 anywhere in your equation, then your entire number line merges into a single point. That means all the numbers will become equal to each other. The laws of your mathematics will break down. Secondly, your number line can also collapse if you break some fundamental properties of mathematics. For example, like you're doing here, so what was the biggest mistake made here? When we said that power to iota pi is equal to e to the power 0, this statement is correct, but the conclusion we drew from it, that since the base is the same, the property of exponents says that if the bases are the same, then the powers must be equal to each other. That is, 2 iota pi equals 0. Actually, this statement is incorrect. Well, now you might say, how can this be wrong? We've been learning this rule since childhood. So I would say, yes, these rules are absolutely correct, but they are only valid for real numbers. These rules are only valid when you are talking about real numbers. If you talk about real numbers, then e to the power x equals e to the power y. If that's the case, then x will be equal to y. That's absolutely correct, but when it comes to complex numbers, the exponential function is a periodic function in complex numbers, meaning their values repeat. But in the case of real numbers, the values do not repeat. Understand it this way. Whenever your exponential function has real values, what will happen is that the function will grow exponentially. Its value will keep increasing continuously. That means the value of e to the power x will never repeat. its value will always keep increasing. But when you multiply a complex number in the exponential function, that is, when you multiply by iota, you find that the function which was previously growing exponentially now starts rotating along a circular path. This means that due to the complex number, the function now has a periodicity where its values repeat along a circular path after a certain interval. In fact, let's see what rule applies in the case of a complex number here. E raised to the power of z plus 2 iota pi. Here, k can be any integer, so actually, this 2 iota pi k indicates the periodicity of this function. So when we say that e to the power of 2 iota pi equals e to the power of 0, it doesn't mean that 2 iota pi equals 0. So it means that 2 iota pi equals 0 plus 2 iota pi k. If we take k equal to 1, then 2 iota pi equals 2 iota pi. This statement is absolutely correct, and it also confirms that e to the power of 2 iota pi equals e to the power of 0 equals 1. But saying that 2 iota pi equals 0 is wrong, because actually this statement is ignoring periodicity. Actually, e to the power of 2 iota pi and e to the power of 0 are the same, because e to the power of 0 and e to the power of 2 iota pi have the same value. This repeats the same values in the complex plane. Let's understand this with a practical example. Look at a clock. Now, we know that complex exponentials move in a circle, just like the second hand of a clock moves. After a full rotation, that is, after 2p, it comes back to the same spot. For example, if you start at 12 o'clock, when your clock completes a 2pi rotation, that is, a full 360 degrees, it comes back to 12 o'clock again. So, let's consider the 12 o'clock position on the clock as e to the power 0, whose value is obviously 1. Now when you do a 2pi rotation, that is, after completing a full circle, you come back to 12 o'clock, in this case too, our value becomes equal to e to the power 0, which means it becomes 1. Similarly, if you complete another circle, it will again be 12 o'clock. But what will your value be this time? E to the power 4 iota pi, but its value will also be 1. Now saying that e to the power 2 iota pi is equal to e to the power 0, and from this concluding that 2 iota pi is equal to 0, saying this is exactly like saying that the time after 2 hours and after 0 hours is the same, meaning 2 hours is equal to 0. Actually, this statement itself is wrong. Why? Because the clock repeats itself. The values are the same, but their periodicity is different. You can check this in another way as well. Let's assume that 2 is equal to 0. Then either 2 pi is equal to 0 or I is equal to 0. But we know that 2 pi cannot be 0 because the value of pi is approximately 3.14, which is a positive number. And that's a fundamental truth in mathematics. So does this mean that I could be equal to 0? The answer is no, because we know that iota is defined as square root of -1. So how can the square root of -1 be equal to 0? That's a contradiction. So from here too, you can see that 2i pi cannot be equal to 0. This means our assumption that 2i pi equals 0 was wrong. Our entire logic fell apart here, and when we use this logic, we get some very weird results in mathematics, like 1 equals 2. This means there was a mistake somewhere in our logic, and that mistake was that we were ignoring the periodicity of the complex exponent. We were applying the properties of real numbers to complex numbers. That's why I always tell you that complex numbers are actually very beautiful, but you have to be very careful when dealing with them. If you're not careful, you'll keep encountering such paradoxes in mathematics. And the behavior of E itself is quite amazing. When there's no imaginary number in the power, the values never repeat. The values keep increasing, the expansion keeps growing up to infinity, but just by multiplying by one imaginary number, the values keep repeating, just like time repeats on a clock. The fact that the same value appears does not at all imply that the periodicity is the same. For example, if it's 12 o'clock today, it will be 12 o'clock again tomorrow. The values are the same, but it would be wrong to say that no time has passed. So if that's wrong, then saying 2i pi equals 0 is also wrong, unless and until you consider periodicity. So I think your doubt should be cleared now. That's all for today's video. We'll meet in the next video. Until then, like this video, share it with your friends, and if you haven't subscribed to our channel yet, do subscribe so you don't miss any future updates.